All right, how's it going? Welcome back to another video here in the series on linear algebra. So far, we have been talking a lot about elements of a vector space, which we call vectors, right? And just to quickly recap what we have been doing in this section so far, we have first introduced at the very beginning what a vector space is as an algebraic object. And then we mentioned that its elements, the elements of a vector space, are called vectors. And according to their definition, we can think of them as things that can be added to other vectors through vector addition and can be multiplied by, real numbers through scalar multiplication. So we defined what these things called vectors were, and then we also gained an intuition for them as well, right? By thinking of them as an arrow pointing somewhere in space. And then after that, we went through various additional operations beyond just vector addition and scalar multiplication, like these various products that we could have, right? Where we were talking about dot products, cross products, triple scalar products, triple vector products, and all these operations that can be composed fundamentally from vector addition and scalar multiplication. To really get an understanding of how different elements of the vector space, how different vectors can interact with each other. Then we went through the idea of talking about basis vectors, where writing a vector in a given basis is writing it, we can think of it as writing it in a specific language specified by the basis. And then just recently we talked about suffix notation or index notation, Einstein's summation notation, whatever you want to call it, where we can use a more compact way of writing out vector equations. And we saw that by using Einstein's summation notation, it is a convenient way of proving various vector identities. So that, is kind of just a summary of this entire section that we've been working on so far. And the one last thing that we're going to do before we say, okay, we've now looked at the elements of a vector space in a lot of detail, is we want to take a more practical look at vectors. A lot of what we have been doing so far has been very much just understanding how vectors can interact with each other, but especially for people that are in applied math or physics or engineering or interested in related fields, computer science, whatever, we are also interested in solving problems involving vectors. And I know that at least when I took my first physics class or calc-based physics class, the very first thing that they had us do was to understand what vectors were, according to the physics definition, at least, these things with a magnitude and a direction, and how to solve equations involving vectors. So that is going to be what we are focused on in this video for kind of like the final sort of topic in this section here, is we want to say, how can we actually solve vector equations in a compact manner? But before we jump into that, I want to make sure that we have a good visual intuition for what it means to have a certain, or to have a vector equation of a specific form. Okay, so we're going to first go through some visual ways of understanding vector equations, and then once we have a good understanding of what a vector equation represents visually, by saying, we can look at an equation and say, okay, that looks like the equation of a line or the equation of a plane or something like that. Then we're going to go through examples for how to actually solve vector equations. Okay, so hopefully that makes sense, at least for what we're going to be covering here. Now, let's get started with the first part of it, just gaining a visual understanding when we see certain vector equations. What I'm going to do is I'm going to write out, the first topic in looking at visual representations for a vector equation. And we're going to first look at the equation of a line using vectors. So let's go through that now. Okay, so let's start out with the equation of a line. And to do this, I want to start out with stuff that we should already be familiar with, which is how to write out the equation of a line just from standard introductory algebra, where we're not considering vectors or anything like that. It's purely if we have maybe let me even draw this out. If we have an xy plane, we have x and y, and if we have some line like this, maybe I should draw it a little bit more generally, so it's not passing through the origin. But if we have our xy plane, then maybe if we have a line like this, and we know that it has a slope or a steepness of m, and it passes through the point B, or I guess, yeah, B, then we can come up with an equation to describe this line, which hopefully we are all familiar with, the slope-intercept form, y equals mx plus b, right? This should be something that we already know. Now, the question is, how do we take this picture of a line and just generalize it to vectors, whether we're working in 2 dimensions, 3 dimensions, or whatever we're working in? And to do that, what I'd like to first do is to just rewrite this equation using slightly different notation, but still writing out just the slope-intercept form for this equation right here. So rather than writing y equals mx plus b, I'm just going to replace the letter x with the letter t. And this by itself doesn't do anything, but the idea is, for why I'm doing this, is because I want to relate this equation to a physical example. Let's say that y represents if this is like the y-axis, the up and down axis, let's say that we're looking at the up and down, or the vertical position of something, as a function of t, a function of time, okay? And m would describe how fast something's position is changing, or in other words, what its speed is. And then b would represent kind of its starting vertical position. And on this graph right here, I guess the starting position would be right above the origin, right? So the idea is that hopefully it makes sense that we could use the slope-intercept form of an equation to describe the vertical position of anything as a function of time. Now, I also want to say that we could do the same thing, not just with the vertical position, but we could do this with the horizontal position as well. We could say that we also have x equals mt plus b to measure the horizontal position of something as a function of time. And maybe think of, you can think of literally whatever you want, right? But maybe if you're imagining like a little fly buzzing around, it's buzzing in the vertical direction and the horizontal direction, and you're measuring its position as a function of time. Now, you can imagine if you have a fly that's just kind of buzzing around, that the vertical position, y, and the horizontal position, x, they might not be the same. Maybe in one instance, the fly wants to move more in the vertical position than the horizontal position, or vice versa. Maybe there's another time where it wants to move a lot in the horizontal direction, but not very much in the vertical direction. The idea behind me saying that is that because we have two different independent directions that we're moving in, they will each have their own respective equations, and the value for the slope or the speed along those directions might be different. So we might have to denote m here as maybe m1 and here as m2. And they could also have different starting positions. Maybe the fly starts a little bit above the origin along the y-axis, but for the x-axis, maybe it starts a little bit, I guess, below the origin. Maybe it starts at -1, 0, for example. So what I'm trying to say is that they might also have different starting points, different intercepts. So we'd have to also denote b1 and b2. And you can imagine we could do the exact same thing if we were to consider the z direction. So maybe the fly's moving in 3 dimensions. So we'd also have z equals maybe m3 times t plus a third intercept. Okay. And hopefully by writing out 3 equations of this form, we can start to see how we can write out the general equation of a line using vectors. Rather than writing out 3 equations, I'm just going to combine everything into vectors. So we're going to have this left-hand side, which is going to contain a vector x with, I guess, 3 components, x, y, z. And that's going to equal 3 components of m. So it looks like there's this vector that represents a slope almost. So m1, m2, and m3 times whatever the independent variable is, in our case, t, or time. And then plus a vector to represent the various different intercepts that we have. So b1, b2, and b3. Okay. And if we were to maybe not write out column vectors, but instead we were going to write out write this out using a little more compact notation, maybe I'll describe this left-hand side column vector as just vector x. So x with a hat over it. So vector x represents this column vector x, y, z. And then maybe this column vector we'll conveniently name m times t plus a vector b. So it turns out that we can use vector notation to essentially just generalize what we already know from Algebra 1. Now, it turns out there is another slightly more compact way of writing out the equation of a line, even though this by itself would be a perfectly good equation. And as I'm doing this, I'm thinking I want to avoid confusion in a couple of minutes, I want to write out vector r instead. So basically r with the hat over it is just going to be x, y, and z. And a lot of times we'll see vector r in physics used to denote the 3-dimensional position of something. So r is equal to mt plus b. Now, what we can end up doing is we can take this equation and apply one of the vector products that we've learned about so far. Conveniently, the cross product if we're working in R3. And what I'd like to do is I'd like to just take the cross product of both sides of the equation with the vector m. So let's see what happens when we do that. So if I have this as my starting equation and I cross both sides with the vector m, this becomes my left-hand side. And then on my right-hand side, I'm going to get mt plus b cross m, like this. Now, one of the properties of the cross product is that we can distribute the individual, I guess, cross m into both terms. So we're still going to have the same left-hand side of r cross m equals this first term, which is going to be m times t cross m plus b cross m, like this. Okay. And one of the properties of the cross product that hopefully we remember is that, and maybe I should even write this out to make sure that we have this in our head. I'm going to try to figure out where I should write this. Maybe I'll write it up here, is that a cross b, if we have 2 vectors in R3, a cross b, that equals the magnitude of a times the magnitude of b times the sine of the angle between them, and it points in a normal direction, or a direction perpendicular to both a and b. But what happens if in this first term right here, both inputs into the cross product are essentially the same vector? We have t, which scales the first vector, but otherwise they're the same vector. What is the angle between a vector and itself? Well, that's just 0, right? So therefore the sine of 0 is just 0, so any vector crossed with itself, or any vector crossed with a scalar multiple of that same vector, will just produce 0. Therefore, this term cancels out, and what we're left with is r cross m equals b cross m, like this. And what I'm trying to get at is that when we see vector equations of this specific form, where we have r cross m equals b cross m, and we're asked to solve for whatever r is. What that is telling us inherently is that this equation describes the equation of a line that is, when we say has a slope of m, basically, if we think of any two lines that have the same slope, what would that mean? That means maybe we have this first line right here and then another line with the same slope. That would indicate that these two lines are parallel, right? So same idea is just going to apply here. This equation describes the equation of a line that is parallel to m, whatever that vector m is, and passes through the y-intercept point, vector b. Okay, so that is how we can physically and intuitively understand what this means whenever we see an equation of this form. All right. Hopefully this makes sense how we obtain this equation, and hopefully we can imagine that whenever this shows up, we can simply say, oh, well that's physically what is going on, rather than having sort of this abstract equation of symbols. All right. So yeah, hopefully this makes sense, and this is only, I guess, for the equation of a line. Next thing we're going to go on to before actually solving these types of equations is to look at an equation of a plane. So I'm going to erase, I think, most of this. We'll keep the boxed equations up right here, and then we'll do the equation of a plane on the other half. Okay, so now moving on to the equation of a plane. And to do this, what I'd like to do is something similar to the equation of a line, where we first start out with this visual picture and then sort of construct the equation from that visual picture. So let me try to just draw an example plane, whatever this plane might be. And we can imagine that this plane exists in three-dimensional space. And the first thing that we would need to do if we were to ask the question, how would we describe the equation of this plane, is the first thing we could do is we could say that whatever this plane is, wherever it's located in space and however it's oriented, there will always be a normal direction associated with this plane. And here's what I mean by a normal direction, because we might be asking ourselves, how does this piece of paper have a direction? And what I mean by a normal direction is I can draw an arrow, and hopefully we can imagine this arrow starts in the middle of the sheet and then it just points directly upwards. And this arrow forms a right angle with any other arrow lying in the plane. So let's say now, for example, this dotted arrow is in the plane. This would form a 90 degrees, hence making it normal or a perpendicular vector. Same thing with maybe this arrow right here. That would also form a right angle. And any dotted arrow that I draw that lies within the plane will make a 90-degree angle. It will be perpendicular to what's called this normal vector. We can call this n. Okay? So what we can do is we can use the normal vector to specify how the plane is oriented in space. You can imagine if we were to tilt this plane, that will in turn tilt the normal vector. And maybe it's easiest to see this where we have sort of an actual example of a plane, which is just this textbook right here. This could be the surface, the plane itself, and this whiteboard marker could represent the normal vector to the surface. And you can imagine that as I rotate this plane, I am in turn constantly changing the value of what the normal vector is. I am constantly changing the coordinates of what this black marker would be as I rotate it in space. So specifying the normal vector, I guess what this marker would be, would specify, I guess, the orientation of the plane. Now, let's say that we've done that. That is our first step. Let's say we've said, okay, this arrow right here, being this whiteboard marker, is the normal direction, and therefore the plane is is oriented like this. Now, there's still some uncertainty as to what the plane could be, because even though we said this is where the normal vector points, it points in this direction, we did not specify maybe the exact location. In other words, this vector could still point in the direction that it is pointing in while we translate this book in space. Not rotate it, because we've already fixed the direction, but we could translate it so that the vector does not change its direction in space. It only changes its physical position going from one position to another. So the second sort of piece to the puzzle that we would need to specify the equation of a plane is what we call a fixed point. And a fixed point is simply going to be represented by some vector. And let's see how this works. I think the best way to do this is to, let's imagine that this plane is somewhat far from the origin. And maybe let's say this is my, this is my three-dimensional graph down here, where maybe we have X, Y, and Z. So this would be the origin, and this would be the plane that's, I guess, further to the right, further up, and I don't know, somewhere forward or into the page. But this is where the plane is relative to the origin. And by a fixed point, we're simply going to represent a fixed point on the plane, meaning some point in the plane, by some vector in three-dimensional space. Here's what I mean. If this happens to be my fixed point, I can draw an arrow from the origin out to this point, like this. And this vector I could call B. This could be my fixed point, okay? So what I claim is that with specifying the normal vector to tell us the orientation and to specify one point, which we're going to call a fixed point in the plane, we can construct the equation of all of the points that are contained within this plane. Let's say too that I want to call this plane maybe uppercase P for plane. What I can then do is I can say, all right, let me just take some point, some other point that is contained within P. Maybe this point right here. And I can just arbitrarily call this X. And this, if B was this point in the plane, and it was represented by a vector going from the origin out to the point, X could also be represented as a vector as well, just with its own vector going from the origin out to here. So what I'm going to do is I'm going to say that if I have some vector X that is in my plane, or I should say let me be more specific. If I have some point X that is contained in the plane, what I can do is I can construct a corresponding vector that lies specifically within this plane. It was incorrect of me to write that X was in the plane because X, as a vector, is the arrow pointing from here out to here. It's only the very tip, this point, that lies in the sheet of paper. What I want to do, though, is I want to draw an arrow that actually lies within the sheet of paper, so lies on this 2D surface here. And the way that I could do that is through vector subtraction. So vector subtraction goes from the tip of one vector to the tip of another vector. So drawing this vector, and you can imagine if this is a point in the plane, and if this is a point in the plane, I'm just drawing a line that connects 2 points in the plane. So therefore, this arrow, this resulting connecting arrow between X and B must lie within the plane. And we would call this X minus B, like this. So what I actually meant to write was that this resulting vector, X minus B, is an element, or it lies within the plane P. Okay? So hopefully that makes sense. That whatever point I have, I can specify X to be this point, this point, this point, this point. Whatever I specify X to be, I know that X minus my fixed point is going to be in the plane. Now, to get this in a form that is somewhat similar to this, what we can do is we can then in turn take the dot product between the normal vector and this quantity right here and see what we get. So let's do that. Let's take whatever this resulting vector is, x minus b, this arrow that lies specifically within the plane. Let's take this x minus b vector and dot it with the normal vector. Let's just quickly remind ourselves what it means to take the dot product. If I have two vectors a dot b, that's going to be the magnitude of a times the magnitude of b times the cosine of the angle between them. Now, what do we know about the angle between x minus b and the normal vector? Well, since the normal vector is going to be perpendicular to any vector that lies in the plane, in the sheet of paper, and x minus b lies in this plane, or this sheet of paper, we know that x minus b and n are going to be perpendicular to each other. And by the geometric definition of the dot product right here, that tells us that theta is going to be 90, and the cosine of 90 is 0, so because these two vectors are perpendicular, their dot product is 0. So we now have an equation that can describe all the points that lie in a plane. And then we can just do something relatively similar to what we have over here. We can first distribute the dot n into both terms, and then we can just add, or let's do that first. So we get x dot n minus b dot n equals 0. And then you can imagine if we just added b dot n over to the other side, we get that x dot n equals b dot n. And this right here would represent the equation of a plane with a normal vector n and a fixed point b. Okay. So we kind of see some parallels that are between this equation right here and this equation right here. And maybe to make it even more, I guess, analogous, you can imagine if I called some point in the plane to be r and the normal vector to be m, then we would have r dot m equals b dot m for a plane. And then for a line, we have r cross m equals b cross m for a line. Okay. So a very similar structure, but we can see that depending on what type of vector product we use, that corresponds to a different visual picture. Hopefully this makes sense in how we were able to use our visual to construct an equation. Okay. Now, since we have come up with a couple of visualizations, or I guess ways to represent a line or a plane in three-dimensional space, what we now want to do is we want to say, okay, let's take these visual pictures that we have and use those to help us actually solve vector equations. Okay. So, excuse me, my voice is starting to go again, unfortunately. What I'm going to do is I'm going to erase the board and just go through an example problem of showing how to solve a vector equation. And then we're going to call it for this video. Okay, so now to get on, I guess, to the main goal of this video is say, all right, let's actually try to solve vector equations and show some general strategies for how to solve vector equations. And we'll get practice with this too on the problem sets. There are multiple problems involving where they're going to ask you to solve vector equations. And to do this, a similar thing to what we've been doing earlier is I want to relate something like this to something that we already know how to do. So let's say we have the equation 3t plus 4 equals 12 or something like that. Or actually, let me do this. I'll say 3r plus 4 equals 12. Typically, you know what? Normally in algebra, they always call it x, right? So 3x plus 4 equals 12. And what they might ask you to do is when they ask you to solve this equation, what are they really asking for? Well, they're asking you to solve for the value of x. And you could go through the process, or you learn various techniques to solve for x. You subtract 4 to the other side to get 3x equals 8, and then you divide by 3 to get that x equals 8/3, right? So there are these techniques that we learn that we can use to solve for x, and we're just going to do something similar here. I would have written the vector x, but I have cross products inherently, and writing vector x on the board in addition with cross products I think can be a bit confusing, so I wanted to kind of steer clear from that. So the main idea though is to solve for the variable, and rather than calling it a vector x, I'm calling it a vector r. So this is the equation that we have, r minus r cross a cross b equals the vector c. And then the goal, and maybe let me just write this out real quick. The goal is to get the vector r equals something on the right-hand side, and we get r equals something by itself. And whatever this something is, it is allowed to contain the vector a, the vector b, and the vector c. These all act as constants in a vector equation, but it cannot have the vector r on this side. Just like with an algebraic equation, if we're asked to solve for x, we can't have x equals 2x plus 4. I mean, I guess we could have that inherently, right? But the equation would not be solved if we had x equals something with x, something also containing x on the right-hand side. The way that this gets solved is that you get x equals -4. You get x by itself, and then the right-hand side does not contain the variable. So same idea here. If we're solving for r, we want to get r equals something that's not containing r. Okay, so hopefully that makes sense. When they ask you to solve a vector equation, that's really what they're asking you to do. Now, how would we go about solving this vector equation right here? Well, one technique that we can use is we can apply a vector identity. And I think we actually went through this in the last video, where this quantity that I'll put in brackets right here is called the triple vector product. And we showed in the last video, using Einstein's summation notation, how to rewrite this triple vector product as a combination of quantities involving dot products. So let's just remind ourselves what that looks like. So in general, and this isn't going to be the exact, the same letters here, but if we have 3 vectors A, B, and C, so A cross B cross C, kind of like the same structure that we have here, that is going to equal, let's see, and then, because I don't remember this even myself, let's see, this is going to equal -c times A dot B, like this, and then, or actually, a better way of writing this is -A times B dot C, yeah, plus B times A dot C, like this. Okay, so you could go through Einstein's summation notation to actually prove this, but let me just make sure that the signs are correct. That looks right. But this is a vector identity. So this triple vector product can be re-expressed as this right-hand side right here. So that's what we're going to do as the first step. We're just going to take this triple vector product, this quantity in brackets, and replace this triple vector product with the corresponding right-hand side. So let's see what that looks like. Taking this equation, we're still going to have r minus something. And now we're just going to substitute this in, but rather than having A, B, and C here, we're going to have R, A, and B, which admittedly might be a little bit confusing at first, but let's see what this is going to look like. So R cross A, I should actually just use different letters to make this, so I don't have A's and B's in different spots, right? So let me just call this M, replace every A with an M. I'm doing this on the fly. Let's call B N. And it doesn't matter what we call the vectors, of course, right? We can call it whatever we want. And everywhere with B, I'm going to have an N. And then there's no C in here, so we'll keep the C in there. Okay, this is a little bit more clear. So rather than having R cross A cross B, everywhere where I see, or R is going to look like M, A is going to look like N, and B is going to look like C. So instead of negative M, I'm going to have negative R. I hope what I'm doing makes sense. This is a general identity that I'm applying to this equation. And then N dot C is going to be A dot B, like that, plus N, which is the vector A, and then M dot C is R dot B. Okay. That is this quantity right here in brackets that still equals the vector C on the right-hand side. I admittedly, I might have made that a little more confusing than that needed to be. The main idea is we're just taking this quantity right here and applying the general vector identity for the triple vector product. And this is what we end up getting. Now, when I do this, I'm just going to I guess, distribute the sign in here. So negative times a negative gives me a positive, and negative times a positive gives me a negative. So this is what my vector equation should look like. Okay. And now, again, let's keep in mind what the overall goal here is. And what I would like to do is I'd like to get R by itself. And to do that, notice in the first two terms, I have a factor of vector R. And vector R in both of these two terms is multiplied by some constant. Here we have R times the number 1, and here we have R times the quantity A dot B. And because A dot B is just a scalar, this is just some number times R. So what I can do is I can say, let's take out a factor of R in each of these terms, and then just work with the remaining scalars that are left over. So we have R times 1 plus A dot B, like this. And then we still have this additional term, minus A times R dot B equals C, like this. So we're slowly working through the process of, I guess, isolating R. But notice that there's still a problematic term. There's still a term in this equation that prevents us from being able to write R equals something. And that problematic term is this guy right here. And we should ask ourselves, why is this problematic? This is a problematic term because R is entangled with B through the dot product. We want to ideally eliminate this in some way, shape, or form. And one of the general techniques that we can use, one of the general techniques that we can use and that you will end up using in the problem set is we can take dot products and cross products with various different vectors. And if we choose our dot products and cross products correctly and cleverly, we can help simplify the equation. Because I already know how to solve this equation, we're just going to tell you what we would need to, I guess, what we would need to either take a dot product with or a cross product with, but we'll see that that stuff will simplify. So what I want to do is I want to take this entire equation and take the dot product, not the cross product, but the dot product with the vector B. And when I do that, let's see what we get. And maybe actually, yeah, we'll do that. So if I do that, then each term is going to get dotted with the vector B. So this first term gets dotted with the vector B. The second term gets dotted with the vector B. And the third term gets dotted with the vector B. Notice that the order in which I'm taking the dot product doesn't matter because the dot product is a symmetric operation. B dot R is the same as R dot B. Okay. And now let's take a look at what we actually have when we do this, when we apply this specific operation to the equation. What we have is we have if we were to distribute b dot r into this term in brackets, we would have b dot r times 1 plus b dot r times a dot b minus b dot a times r dot b equals c dot b. But notice that let's look at the second term and this third term right here. The second term has a factor of a dot b, and then the third term has a factor of b dot a, which is the same thing. And then both terms have a factor of b dot r and r dot b. So this quantity, and let me maybe explicitly write this out. So we would have b dot r times 1 plus b dot r times a dot b, that's this term right here, minus b dot a times r dot b, that's this term right here, running out of room, equals c dot b. And this term right here is exactly the same thing as this term. So those two terms end up canceling. And we might say, okay, cool. Now we get this simplified equation, and let's see what's left over. We still have this first term, b dot r, is equal to the same right-hand side, c dot b. Now, why was this important? It seems like we're just performing these algebraic manipulations. Well, let's remind ourselves by going back to this equation right here. We said that this equation seemed to be okay, except there was this problematic term we talked about, this r dot b. R was written in terms of r dot b, and we wanted to eliminate that somehow. And now that we have taken the dot product with the vector b to every single term, we see that r dot b is actually just equal to c dot b. And that's really good, right? Because if we want to get r by itself, this is a way of unentangling the dot product, right? I guess I shouldn't say unentangling, but rather than writing the dot product r dot b that contains the vector r, it is identical to replacing the vector r with the vector c. And as long as it doesn't matter that we have c dot b, we just want to get r by itself. These are just two vector constants in the overall vector equation. So now let's take this identity that we just established and plug it back into the equation that we originally had. And that would be this equation right here. And there's kind of a lot going on. So maybe what I'm going to do, I'm just going to quickly erase this line and below. What this line was just taking this equation, maybe I'll put a star. This was the equation, and then we took the star equation and applied the dot product with the vector b with everything, and from there on out it was just manipulations. But this was really the equation that we left off at before we performed the manipulations of applying the dot product. So this is the equation that we had, but now rather than writing r dot b, we just established that r dot b is the same thing as c dot b. So I can replace r dot b with c dot b. And now that I've done that, now I am successfully able to isolate r by itself. Let's see how to do that. Let's first get just all the terms that contain the vector r by itself on the left-hand side. So I have r plus r times a dot b. And then get everything that doesn't contain the vector r on the right-hand side. So I have c plus this quantity right here. C plus a times c dot b, like this. And then we can just do something similar to what we did previously. We could take out a factor of r, so this ends up becoming r times 1 plus a dot b. Right, going from here to here is just taking out a factor of r, and then this is simply some scalar. A dot b is just a number, and 1 plus a number is just a number. So by dividing the quantity in brackets, we're just dividing a number over to the right-hand side, and this allows us to isolate for r. So we're going to get that r equals this in our numerator, c plus a times c dot b, divided by the term in brackets, which is our denominator, 1 plus a dot b, like this. So we see that some of the same algebraic or similar algebraic techniques apply, like when we're just solving for x in introductory algebra, right? We can apply some convenient operation to both sides of the equation. And maybe let me just write this here. If we had x plus 2 equals 6, a convenient operation we could apply to both sides of the equation is we could subtract 2 from both sides. And that causes the 2's to cancel, kind of like how some of the terms canceled when we took the dot product on both sides. And then you eventually, after applying these manipulations, you get x equals 4. Same idea applies here. If you apply convenient dot products and cross products, you'll see that stuff will eventually cancel out, and we're left with r equals a bunch of terms on the right-hand side, but importantly, all of these terms are simply constants. None of them actually contain the vector r. So this is how we can solve one example of solving vector equations. Okay, I hope this is clear. And you'll get more practice with this as well when you work through some of the problems on the problem set. But yeah, that is going to be it for this video. My voice is starting to go again. But that takes care of the elements of the vector space, talking about these things called vectors. We've done a lot with vectors, right? As we will see maybe going forward into the next video, maybe I'll just very quickly give it like some foreshadowing to what that might be. The analogy to what we will be doing next is if you go back to when we started learning about sets, or whenever you started learning about sets, you first start learning about the elements of a set, kind of like how we're learning about the elements of a vector space. And usually one of the next things right after that is you say, how can we map between various sets? If this is a set A and a set B, how can we take the elements of A and connect them somehow to the elements of B? And usually that's through some sort of thing called a function, right? And learning about taking that next step. So now learning about not just what are the elements of a vector space, but how can we map between vector spaces is going to be our next overall goal in understanding vector spaces and how to work with them as algebraic objects. So, but we'll save that, of course, for next time. Thanks so much for watching, and I will see you guys again in the next one.